So we can do spiking experiments where we actually utilize our products instead of styrene as a reactant to try to interrogate this reaction pathway. And we can eliminate different pathways, but also still make it a slightly more complicated system to show which products can actually derive from which species. And we actually see that that nucleophilic attack between the epoxide and the benzaldehyde is not relevant at these conditions. So the question is, why do we not see any of this phenylacetaldehyd and we only see the glycol? And so we can think back to what's actually catalyzing these reactions. There we go. The styrene glycol formation is actually acid catalyzed or acid mediated, whereas the phenylacetaldehyde is base mediated. And so if we look at distributions of acid and base sites from TPD, we can see that for both chromium and iron, the acid site densities are much higher than that of the basic site densities, which is consistent with the lack of phenylacetaldehyde. And then the higher acid site density that we measure on iron compared to chromium is consistent with the fact that we have very little epoxide being formed, or very little epoxide being remaining in our system. Any that is formed is directly converted to the glycol due to the presence of residual water as well as water that's co-fed with, or that is with the hydrogen peroxide oxidant. Okay, so that's at the pathway level, but what's the catalyst actually doing? So first we have to utilize our oxidant that we're feeding into the system, and that's hydrogen peroxide. So it first undergoes an adsorption onto a coordinatively unsaturated metal site. It then activates to create some surface-derived intermediate. It can undergo unwanted decomposition of hydrogen peroxide to create water and oxygen. And actually at higher temperatures we see a significant amount of this with actually bubbling of gas through our liquid, consistent with oxygen being produced. But at lower temperatures we can actually try to trap and react this reactive intermediate. It would undergo a reaction with our styrene to create one of our two transition states to create our primary products, which then undergo conversions of the secondary products we've already discussed. And so the identity of both this reactive intermediate and the transition state, right, the kinetically relevant barrier of the species that we're actually interested in, we can start to postulate what those species look like. And so for the metallocycle transition states, it's postulated that a 4-coordinate transition state leads to this benzaldehyde, whereas a pentacoordinate transition state leads to this to the epoxide product. But then what do we actually have on our surface? And these could be a variety of different hydrogen peroxide derived surface intermediates. But first you have to actually probe to make sure that it is actually occurring on the surface and not some sort of bulk phase radical chemistry. And so we probe that by utilizing a radical trapping agent that goes after either the superoxide or the hydroperoxo radicals. So this NBT in the presence of those radicals will create this monoformazan, which is purple in color. We can look at that in the UV vis in the absence of catalyst and see this deep purple appear, but in the presence of either one of our catalysts, we do not see the signature stretch for that in our UV vis, indicative of the fact that we don't have any bulk phase radicals, or as this is a fairly large molecule, so it's not able to access the pores, it's just reading what's back out into the solution phase. So if we think about, okay, what other radicals are around, or maybe something that is small enough that can actually get closer to the catalyst site. And so we look at methanol as a quenching agent that could go after hydroxyl radicals. And so it would form this formic acid as a byproduct. However, when we run our reaction for the iron analog in methanol, instead of seeing a suppression of rates, we actually see an increased rate, though we see very similar product distributions indicative of the fact that we might just have some solvation or some solvent effects, but not really changing relative selectivities of our transition states. However, in the case of chromium, we have both that increase in our rate as well as a slight distribution change within our products. Much more of our products are those primary styrene or the epoxide as well as the benzaldehyde, and much more benzaldehyde by fraction in this case. The other thing to note is that when we look at our reaction broth after 2 hours in these two different solvents for chromium, we see a fairly clear color liquid for the methanol, but this much darker purple color that we'll come back to in a bit. But this is most likely consistent with, or if you play around with the periodic table and transition metals, you might know that this is consistent with a chromium species. So we'll get back to that in a few slides. So we don't think that there's bulk phase radicals doing the chemistry, but then what is actually doing the chemistry on our surface? And so what we did was we used a computer to try to postulate what's happening. And so Sam did calculations not on MIL 101, but instead on MIL 88B, which is a similar polymorph of this framework, the same linker, same trimeric oxide node, just a little bit different structure. Ooh, sorry. So he looks at initially the absorption of hydrogen peroxide onto a core natively unsaturated site. This then can either undergo a hydride abstraction transition state to create the hydroperoxide, or oxygen-oxygen bond breakage to create the two hydroxide intermediates. These have fairly similar transition state energies or barriers, though the hydroperoxide is favored by 10 kilojoules per mole. We can then compare that back where it shows that the favorable, thermodynamically favorable product of this activation is that from the hydride transfer step, or for the hydrogen abstraction step to create this hydroperoxide intermediate. And so we haven't done experimental corroboration to probe the identity of these species, but at least suggests that both have very low barriers, but thermodynamically this hydroperoxide might be dominating. So we go back to our full cycle, and if we wrote a rate expression for the production of our oxygenates, you can see quite a mess, something that I could not just fit an elephant, but probably fit the whole zoo. And so we want to try to eliminate some of these terms that aren't really relevant. And so we start to postulate that either a hydrogen peroxide physis or bound species or our hydroperoxide peroxo intermediate is our massy. And so we can look at changing our here activities because we're working in the liquid phase. We look at both iron and chromium changing our styrene concentrations and therefore their activities, and see that there's linear with respect to that. And independent of hydrogen peroxide concentration. And so this suggests that we have a first order expression with respect to styrene, and that we have a massy that's one of these hydrogen peroxide derived reactive intermediates. And so this was looking at the total production of oxygenates, so it's combined for both of these rate constants, but we can also model that based off of the two individual products, and we can extract rate constants from those components as well. And so if we look at now what our barriers are for forming these different products based on here anomaly the same reactive intermediate, we can then compare what those barriers look like in our different solvents. And so we compare our acetonitrile back to the methanol data, and we can see that the delta G here, this is the free energy of formation of the transition state in methanol relative to an acetonitrile for styrene oxide is favored on both catalysts and methanol, consistent with additional hydrogen bonding that can form within this transition state. We also see the same for benzaldehyde, again, allowing for this hydrogen bonding network with this with the now 4-coordinate transition state that has the oxygen-derived intermediate. We can then look at just maybe one of those products, or look at the different products now as a function of the iron catalyst. And if we look now, this is the change in the free energy of formation for the styrene oxide relative to the benzaldehyde. So the same data, just plotted slightly differently. And so it shows that these are positive values indicating that the benzaldehyde is favored in both solvents on iron, and that the difference in the entropy of formation is relative to the fact that you're forming a transition state that has a slightly more flexible tail that can sort of flap within the solvent and create a more disordered network. And so the question is, well, we have these systems, and what does our actual site look like after reaction? And so if we go back to measuring our acid site densities after our chemistry, this is at different reaction temperatures that we studied, we can see that on chromium, our acid site densities increase as a function of reaction relative to the fresh catalyst. And so this is consistent with the fact that we have natively unsaturated sites being generated during our reaction. And when we go back to actually thinking, if you remember that purple that was there, that we actually have these natively unsaturated sites that open, and after many turnovers, we actually have leaching of this chromium into the system, and into the solvent, and those chromium species are actually active and have a different selectivity for our oxidation products. So you can see this is doing after a leach test, so we run the reaction for an hour, remove the solid, and just leave whatever's in the broth. See, we have an increase in our reaction rate, as well as a change in our product distribution. So it really favors those deeper oxidation events to benzoic acid. We can, as I mentioned, we saw the color purple, so we can actually measure that color purple, not just with our eyes, but also with the UV vis spectrometer, and we can see that our leached chromium concentration increases as a function of time, and it actually fits very similarly to a fitted deactivation rate constant at extended times, suggesting that all of our deactivation on the chromium system actually occurs from leaching. When we do a similar analysis on iron, we do still see an increase in our acid site density, which is consistent with a change in our binding at the active site. However, in this case, we don't see any increased reactivity after doing the leach test. We also see very similar product distributions as shown here. And so what this suggests is that even if we do have some leaching that is occurring with our iron, it actually is not, it's not active for this chemistry and not changing our product distribution. And so when we look back to something that we might measure from the amount of orange that's in the system, relative to our deactivation rate constancies, are in different orders of magnitude, and also they're much lower than what we measured in the chromium case. So in the last maybe 30 seconds or so, I want to extend this a bit. So the bulk of this work was looking at MIL 101, so that's using this 1,4-benzene dicarboxylic acid linker. However, we can start to probe these other swaths of our metal organic framework landscape and maybe change the linker to create another zeotype, which is this MIL 101, which has a very similar structure except just different size windows and cages. We can also add in functionality onto that linker as something like an amine group to try to probe now both transport as well as electronic interactions at our active site. And so, briefly comparing MIL 101 and MIL 100, we make these materials, they are as what we say, trust me. And we can also characterize them using Mossbauer, which shows that inherently at the beginning we have are entirely iron 3 sites in these 3 different frameworks. And so when we actually looking at the reaction data, we see that our MIL 101 is actually performing best. This goes back to when we look at our rate constants, we can see that we have an inductive effect of our amine group that allows for increased electron density and then therefore has a lower rate constant in this case. We also see that after reaction, we have some ability of that transformation of those natively unsaturated sites within our MIL 101 framework without the amine, but the amine kind of inhibits that formation. And so in Mossbauer, we actually don't see any of this iron 2 formation. And then consistently, we don't see that iron 2 formation in MIL 100, but the lower rate constant that we measure is actually consistent with the smaller pore size and actually transport limitations of our fairly small styrene molecule to get into the catalyst. And so, there we go. So with that, I'll conclude where we've been utilizing these MOFs as a modular scaffold to look at oxidation chemistry for both iron and chromium analogs, trying to understand both pathway preferences as well as elucidate solvent interactions, think about stability of transition states in our reactive intermediates. And so I'd like to thank my group, funding for some of this work, and also a plug for some of my students, including Rachel, who did the work that I showed today, for some of their talks later in the week or poster sessions, and I'd be happy to take any questions.
We have a question already.
Hi, Michele, great talk. I just had one question, basically. You mentioned counting acid and base sites, and I was curious what you think the local structures of those two types of sites are, and also how the numbers you counted compared on a per chromium or per iron basis.
Yeah, so a little bit unclear in part. It could either be that we have an open site, maybe like a missing, we're trying to probe the difference between when if you have a missing linker or if you have the acid site actually being able to bind to the to the iron node itself. So we aren't quite distinguishing between those two. We have to do a little bit more characterization to determine that. I don't know off the top of my head the ratio of those to our total metal sites, but they're much lower.
Hey, Michele. I really enjoyed the talk. I was curious what strategies you have in mind for trying to assess the number of feedbacks or missing linkers that you share your thoughts?
Yeah, so some of it can be related to the hydroscopic nature of these materials, and so looking at how much water they take up in their native form and how much you can desorb is one way to start to probe the open sites or the missing linkers in that case. We can also monitor during reaction with NMR the amount of linker that comes off, so it's not just what's there at the beginning, but it's also as a function of reaction. And so I didn't show it here, but looking at what's leached into the broth versus what's left in the solid, we can start to do the analysis to make sure that those are matching up, or if we have more linker coming off in one sample versus more metal being leached.
So I think in the interest of time, we'll move on to the last talk of the session.